College, the American Physical Society, the Institute of Physics, and the Materials Research Society. His research interests include nanomaterials growth, modeling, characterization, and devices. He was awarded the Royal Society Brian Mercer Award for Innovation and the Marie Curie Excellent Award, the Philip Leverhulme Prize, the EU40 Materials Prize, the Royal Society Wolfson Research Merit Award. He is also the chairman of the executive board of the EU Graphene Flagship. Thank you very much, Professor Ferrari, for being here today. It's not the first time in Albania, and we are really very happy to have you as a plenary speaker. So, Professor Ferrari, it's your turn. Thank you very much.
Okay, so yes, you can hear me. Good morning, everybody. And thanks to Arben for the invitation. It's always a pleasure to be here for this conference. Really, Albania, and thanks to Arben, is becoming the center of nanotechnology in the Balkans and a key point of reference for people working in the field. In particular, I mean, as we heard in the opening ceremony, all the main themes ranging from AI to health and so on are relevant to nanotechnology. So I think at this point my talk should have already finished, but I will start. So we were slightly late on the timetable, but I'm not going to be able to catch up much time. So I will try to go through it with a general introduction on layered materials for quantum and photonics, and in particular, I will focus on some biomedical applications at the end. Also, I have to update the CV that Arben used, that was probably a bit out of date. I'm not anymore the chair of the executive board of the Graphene Flagship, but I'm co-chairing a new initiative that is called Innovative Advanced Materials for Europe, that will invest way more money than the Graphene Flagship has done over the past, hopefully 10 years, with 500 million already between 2025 and 2027. And if I have time at the end, even though I will not have time, but I think I will try to make some time to introduce this new initiative that will define the European investments in advanced materials for the next several years, and will be the largest investment in Europe, and probably worldwide, in advanced materials is going to happen. But before going to this, I guess there's no pointer, so I'm going to use this. So we are all familiar with industrial revolutions, and now we are in the period of the so-called fifth industrial revolution, which is not the one before where we discuss about IoT. This is a mass customization and cyber-physical cognitive systems coming together. So it's the era where artificial intelligence is going to be integrated with hardware and also with software, and we are already experiencing this day to day. This is also what is called Industry X.0, and it's a combination of different technology and cyber-physical systems together. There also, in terms of communication, the next step will be the 6G after the 5G. And essentially in 6G communication, we have the convergence of 5G, artificial intelligence, data analytics, and Internet of Things. So this is what is going to happen in the future, and is happening in the future. So the digital devices require more bandwidth. The optical connectivity must improve to satisfy the needs and to reach sustainability. Just look at the difference between the 5G networks and the 2, 3, and 4G evolution. That was not so huge as just the jump from 4 to 5G. And the jump to 6G will be another factor of 1,000. So digitalization, cloud computing, Internet of Things, 5G, 6G, high-performance computing, artificial intelligence are all coming together, and this makes it very exciting for us. We are not software engineers, and this talk is not about software, it's about hardware, but we are material scientists and nanotechnologists, and this evolution brings a lot of challenges that we have to tackle. So high performance, low latency computing will be necessary to bring AI to the cognitive level. And the key for all of this is photonics, to enable clusters of processors and memories to interact together with huge efficiency and low latency, that means high speed. So this is also an important point for sustainability challenges. Already now, a 1-hour Zoom call, it's producing around 300 grams of CO2. But training AI model uses the same energy as the 5 times the average lifetime of a car. And not to speak about mining of Bitcoins that require the average energy used by one American family over 2 years. During COVID, the biggest influence on global emission was not between data and airplanes, was not given by the air industry. Airplanes contributed less than data communication to the global emission. Already now, data communication contributes about 4%, but with the explosion of AI and everything else, it is expected by 2040, this will be around 20%. Planes are, peaking. Yes, it's nice to say, oh, you're taking a private plane, so you're killing the environment and so on. But one person flying a private plane is nothing. While lots of people watching Netflix on the phone, they contribute more. And data are not exchanged for free. And think when Facebook was born, all the servers were in California. This meant that you are here, you took a picture in Tirana, the picture went to California, and then you wanted to show the picture to your friend, the picture went back from California to Tirana. Pictures don't travel for free. They use about 17 picojoule per bit, and there are 180 exabytes of information exchanged every month. This is really the challenge. Google and colleagues are using the same amount of energy that probably 10 times Albania uses as a country to run the data centers. And people don't quite understand this. And this is going to become worse and worse. So this is great because, well, it's bad, but it's great for material science. Something else that people have to remember, especially people who teach in universities, we always consider the Moore's law. People like to cite the Moore's paper. Not many people like to read it. And this paper is available online very easily now. It was not so easily available at the beginning because it was in an internal IBM report. And besides the sketch of what was going to be called the Moore's law, what you also write, very importantly, is it may prove to be more economical to build large systems out of smaller functions, separately packaged and interconnected. So he already said there are two options: either you go smaller and smaller and smaller, or you build large systems out of smaller functions that are packaged together. This is what is happening now with the chiplets. If you look at the plenary of the CEO of NVIDIA in March, he showed this new processor based on a large number of chiplets connected together. The individual chips in the chiplets do not need to realize they are disconnected. They need to think they are in the same place. And in order for this to happen, you need high bandwidth, low latency, and of course, low power, energy efficient communication between them. And Agilent, Tesla, most people don't realize that Tesla is developing new chips for the car. They're not just buying externally, they're designing and building them themselves. And this is something that was published in March from Intel, is the Universal Chiplet Interconnect Express, UCLE, and is a platform developed by Intel whereby third-party users can put together the different chiplets to create new architectures. This is the future. Advanced packaging in chiplets is what is needed. However, what is the problem? To have all the chiplets in a chip believe that they belong to the same structure, they need to communicate very quickly, and now this is done with copper wires. And this is reaching a limit to the point that the next step is the co-integration of electronic and photonics on chip. This is an example of an Intel network switch That's the ASIC, these are the optical fibers, and these are the copper wire arrays. And all the power consumption is happening here, or the vast majority of the power consumption is happening there, and there is a lot of issues there, and all the major companies are hitting this problem. In fact, if you are a subscriber of Optica, I mean the journal of the American Optical Society, in the latest issue there is a set of interviews with a major manufacturer discussing about the role of photonics in AI. Photonics will be key in order to make AI viable because it needs to reduce the power consumption. And this, just to tell you, this design from Intel requires a liquid-cooled system due to the enormous amount of energy that is generated. So that's where graphene comes into play, and graphene is one of the key materials for this. Graphene can work up to 100 Celsius. The high extinction ratio modulation allows the elimination of the post-processing electronics. So going from 17 to 4 picojoule per bit, using graphene to do this eliminates 70% of the power consumption. This is now acknowledged, and graphene is the solution for this. And the graphene detector generates directly a voltage rather than a current, and you only require an amplifier instead of a transimpedance amplifier. So graphene delivers multiple performance improvement with a single technology. It is ultra fast, efficient, compact, low cost, low power consumption, and most importantly, is wavelength agnostic. So the Dirac variance means that the same piece of graphene can work at multiple wavelengths at the same time, unlike what you can do with all traditional technologies, with silicon photonics or other alternatives. So you can do multiplexing for free, and you can massively reduce the costs. So on one end, we have silicon photonics, where we have an active photonic circuit, we have free carrier losses, we have static power consumption. Static power consumption means that in silicon photonics, you consume energy when you transmit a 1, when you transmit a 0, as well as when you transition between 0 and 1. The future is the integration of graphene with silicon photonics. In this case, the silicon will only guide light, while the graphene does all the work in terms of modulation and everything else. There is no static power consumption, so 2/3 of the power is already saved in that way. So this field started a few years ago, in particular with our paper in 2018 that set forward all the vision for that. And once you remove the task from the silicon of doing the active work and you leave it to graphene, it means that the substrate can also be any other passive substrate. So it could be silicon, silicon nitride, glass polymers, and so on. So this is an example of a spin out from Nokia, based in Cambridge, called Emberion, and using graphene-based devices in collaboration with us, already has produced these super pixels of 80 × 60 super pixel. Each pixel works in visible, short, and mid-wave IR. It is the same pixel that works across all the wavelengths. So it's a it's a hyperspectral camera that works and at the wafer scale. Also at the wafer scale, a couple of years ago, we showed this integration. These were 12,000 modulators, 12,000, not 12, working at 20 gigabit per second on a 6-inch wafer. We are now up to 100 gigabit per second on a wafer scale up to 8-inch. And so these are the modulators. I don't know. Yeah, actually the contrast is quite good. You can probably see here, there, and there all the graphene flakes. These graphene are individually grown on the substrate by doing seeding, and then you put all the designs on the top. And recently, the UK government has funded what is called the LMRF, Layered Materials Research Foundry, which is a collaboration between Cornerstone and the Graphene Center to produce 8-inch wafers with designs of modulators and detectors on the top of them. And this is the first wafer, diced wafer that we produced, and soon this will become public facility. for everybody to use. In fact, if everything goes well, and again, thanks a lot to the Spanish government in this case, there should be a good announcement in terms of a photonic pilot facility in Europe in the next few months, and part of the work will also be the integration of graphene. In terms of growth, we are now able to grow these materials on a large scale. This is the closed-coupled showerhead CCS2D MOCVD system from Einstein. Einstein in Cambridge, there used to be a spin-off called Cambridge Nanosystems, and this was then acquired by Einstein. So this system can grow graphene, HBN, and all the other 2D materials on a wafer scale. This is an example of wafer scale growth of WS2. So this is 2-inch and this is 8-inch. You can either grow a single 8-inch wafer or a lot of small 2-inch wafers on the top of the substrate. So let me now switch from the photonics to the quantum field. I direct you to this paper that we published last year on layered materials as a platform for quantum technologies. This afternoon, Meta Tatur is going to give another talk on this, so I will just give you some highlights. So quantum information processing can be done with light, and for this we need single photon sources, and this can be used for quantum encryption, quantum computing, random number generation. And the target is to have these sources to be on demand, pure, with high repetition rate and indistinguishable. So how to get to real-world application? We need the technology to be scalable, electrically triggered, hopefully working at room temperature with good quantum efficiency, good light extraction. We need to integrate these in resonators, and it has to be compatible with current technology. So why single photons in layered materials and layered quantum materials? Because unlike three-dimensional systems like diamond, this is two-dimensional, so all the emitters will be in the same plane. This allows us to create deterministic and scalable arrays of single photon emitters, and then, as mentioned before, we can exploit the know-how to do the integration on optical circuits. So the roadmap here is to understand the physical origin of these emitters. There are still debates on them, modulate these single photon emitters, grow and transfer these layered quantum materials and their heterostructures on a wafer scale, and integrate them with photonic circuits. So this can be shown like this is a single photon emitter, then you have a single photon processor and a single photon detector on the same chip, or if you put a little bit more money in the picture, you get this nicer picture where you have a quantum integrated photonic circuit, QP or QPIC. And this is where a lot of effort and research is nowadays going. In fact, we can summarize the status of layered quantum materials as follows with this graph. So graphene is used in quantum mostly for contacts, but not for emitters. The emitters are transition metadigitated organized PMDs, or hexagonal boron nitride that can work up to room temperature. And then there is the new kid on the block, the Janus materials. Janus materials are those TMDs that are terminated by two different atoms on the top and bottom surface. This creates asymmetries, and this creates a lot of nice effects when it comes to modulation of the emitters. But even more interestingly is the case of heterostructures. By putting layers one on the top of each other, we create a so-called moire physics, moire excitons, which means that the emission wavelength can be tuned just by changing the angle between the two layers. And this field started around 2016. So it's a few years now that this is going on, and it started slow and now it's exploding. And if you look in the literature, we have quantum communication, quantum networks, quantum computing, single photon detector, quantum simulation, quantum sensing, all done with these materials. And again, I point you towards the talk of Meta in the afternoon for this. However, there's not only quantum computing, and something I believe important in the NanoBalkan initiative is the interaction between nanotechnology and health. That's why I want to focus the last part of my talk on this, to say that quantum can also be used for biosensing or for quantum MRI, and what I'm going to talk about now is the use of coherent Raman for chemometric imaging. So if you look at imaging tools for biopsies, optical microscopy is very good and gives the morphology. It provides much better spatial resolution compared to MRI, and it doesn't require samples to be fixed as in electron microscopy. However, it is always or often combined with fluorescence microscopy, where you use markers to increase the sensitivity down to the single molecule level. The problem is that all these fluorescent markers cannot be implemented within certain cells or tissues because it can give a strong perturbation to the system. And if we consider small molecules like peptides, neurotransmitters, and so on, if we put this marker on the top of them and then we study the dynamics, it's not the same having one molecule going around or one molecule with a huge hole on the back going around. We are perturbing the system and we are not studying the pristine situation. And also in clinical application involving live tissue imaging, you don't want to put a lot of markers, dots, and so on in the patient because this is not very good. So what we need is an intrinsic label-free imaging method that do not require any fluorescence molecules. And this can be done by Raman. We are familiar with spontaneous Raman spectroscopy, where we use one laser and then we detect the incoherent thermal vibrations on the samples. But the next step is to do what is called coherent Raman spectroscopy. So instead of using one laser, we use two lasers at the same time, a pump and a Stokes laser, and the difference between the two energies is exactly equal to the frequency that we want to study. So as you can see, in this case, all the vibrations are driven coherently by the two pulse, by the pump and Stokes pulses. But the problem is that we can only see one frequency at a time. So if we keep the pump constant, we will need to sweep the Stokes across different frequencies in order to get this done. What this transition between incoherent to coherent gives is an enhancement of the signal up to 10 to the 10 times, which means you can take entire Raman spectra in microseconds instead of taking them in tens of seconds or in minutes, making it a viable tool for histopathology. How does histopathology work at present? So the doctor takes a sample from you, and then they put some dye on the top of it. The dye is producing a color, and the doctor with the eyes looks in the microscope and says, okay, that's a tumor, that's healthy. And this is not done by solving an equation or anything like that. It's pretty much like the case when you go to a museum and you look at a picture and some art critic is telling you why this picture is so good and so valuable and why another one is not. So it's all about subjective interpretation of the data. And that's why many people, when, especially for tumors, you ask for a second opinion or a third opinion, because literally it is an opinion. It's not second solving on an equation or third solving of the same equation. You go to a doctor, they look at it and say, okay, and the other one look at it and say, okay. And the problem really is not the part that is clearly a tumor, clearly healthy, but is always the interface. Because doing surgery, you want to remove the tumor, but not remove too much, especially if you're looking at brain tumors or things like that. So Raman actually works fine. It has been used for years. And if you just Google, you will find Raman spectra of every sort of tumors already for many, many years ago. And this is just a very, 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 very small table with some summary results. What is the problem? The problem is that it is incredibly slow. Well, it is very slow. So it means that if I take a biopsy of 1 centimeter square, it will take like a week in order to have all the data measured and analyzed, which is clearly not viable. So the goal is to have a fast and broadband coherent Raman microscope that produces images like this, that this image will not be an optical image like in the case of the biopsy, but it's a Raman map, and each pixel corresponds to a Raman spectrum. And then by analyzing the Raman spectra, you can tell if you're a tumor or a normal tissue. So spontaneous Raman is great. It gives you a huge amount of information content, but it's extremely slow. Coherent Raman is usually very quick, but not a lot of information content. So we need to improve both techniques quite significantly to get to a sweet spot where they can be used. So at present, you can buy, if you go to a shop, you can buy a coherent laser system, a coherent Raman system, and the leading manufacturer is Leica. It costs about €1.5 million to buy one of these systems, and the reason why it's so expensive is because you need these lasers that needs to be synchronized and tuned. On the top of it is not just the cost, because in an hospital, an MRI system is very expensive. It's also how it looks like. What they give you is not like a nice and shiny MRI system where you put a patient in it and you click a button. You get an optical table full of lasers and connections and optics, and then you need to get a couple of postdocs to operate it. And for sure, you cannot take this optical table and sort of put it close to the brain of the patient or something like that. So it works, but it's not usable in a clinical environment, besides the fact of being extremely expensive. That's where graphene also comes in, and graphene comes in really in the part related to the Masters Dirac fermions. It's now 20 years since the Nobel Prize, so it's good to remember things that are directly linked to the reason why graphene got the Nobel Prize. So this Dirac cone means that when we have light coming in, I always create an electron-hole pair, whatever frequency I'm using. These electrons, once they are excited, they don't immediately relax. They stay for about 10 or 20 femtoseconds in the excited state. This means that within the next 20 femtoseconds, the next light that comes cannot be absorbed due to Pauli blocking, because we already have the electron pair created. So I need to wait a little bit before the next absorption. So this means that I shine light on graphene, it's a continuous light, and comes up modulated. So how to create these lasers? If we want to build a laser, we put a mirror and another semi-transparent mirror. We put a green medium in the middle, and then we put what is called a Saturov absorber that can be this piece of graphene. So something that absorbs light, saturates, stops, absorbs light, saturates, stop. And if we do that, what we get out is a set of pulses. So a Saturov absorber turns a continuous wave laser into an ultra-fast laser. So this was done already in 2009. So we took some graphene dispersion and some polymer, created a polymer composite, chopped it, and you can see this, the polymer composite on the top of the optical fiber, and included this into a laser setup that I'm not going to discuss in detail. But all of this is very simple and cheap. It's an optical fiber, so there's no alignment. You can shake it and nothing happens. And this is a very, very old movie of 2009, when this first laser was built and packaged, and then you can see the laser pulses on the screen after a photodetector, so not a big deal. The other interesting thing is the Dirac cone in action, because this laser can be tuned continuously due to what I said before. It works on any frequency, so you can see 30 nanometer continuous tuning of the emission, and please note that the limitation here is not graphene, it's the optical fiber, the gain medium. The erbium doped fiber amplifier only works over 30 to 40 nanometer. Graphene will work forever. So let's skip this part and get to this. So because graphene works forever for any wavelength, a few years ago, we did an experiment whereby we said, okay, let's build two lasers at two different frequencies, but use the same piece of graphene in one leg. So not two different pieces of graphene, the same piece of graphene in two lasers, one working at 1 micron and one at 1.5 micron. So what happened is the following. You can see this moving. We switched on the thing. After a few seconds, you will see the pulses coming up. There you are. But you see they are perfectly synchronized between the two lasers. So not only we got mode locking of each individual lasers, but we got perfect synchronization. And the synchronization of the pulses is what you need for the coherent Raman. If the two pulses, pump and stokes, are not synchronized, you will not get a coherent excitation. So this will enable us to build a synchronized laser that could be used for chemical imaging, for medical imaging. So the first test was on beads, polystyrene and PMMA beads. That's very easy. PMMA and PS have different Raman peaks, so you can measure them and clearly identify them in the sample. Then you can put different other ingredients such as olive oil and whatever. And this is, of course, these are artificial samples prepared in the lab. It works quite nice. You already know what you're looking at. But then the proof is in the pudding. Let's look at the real tumor. So this is a mouse fibrosarcoma, and this is the H&E slice. So it's a stained biopsy identified in the traditional technique. We can take the same sample and do our Raman imaging, and you get this label-free stimulated Raman scattering. And now we can plot the different maps at different frequencies, because this is a Raman image, which means by looking at this map and looking at the Raman spectra, we can identify the cancer or the not cancer part by automatically, with no need of a subjective interpretation. So this is another example. On the left, or your left, is the H&E, so which is a picture with nuclei with blobs. On the right is the Raman image. And the Raman image can identify you if you want lipids or the proteins, because if I want to only see the lipids, I say plot the peak of the lipid. If I want to see the protein, I say plot the peak of the protein. And then if I want to see it all together, I say plot all together. This is impossible to do with an H&E slide. And of course, the amount of data that is collected in this biopsy is ginormous. And so you need to integrate AI in order to analyze this extremely large amount of data. And then what you can do is the following. You can take a picture, this SRS is the Raman image, and then you tell your AI, do an AI staining, which means make a picture that looks like an H&E stain for a doctor, because doctors are very traditional. And then you can also have the real H&E stain. I can tell you, if you remove this label, and we did try this with several doctors, with 50% probability they would indicate one or the other. There's not been a single doctor that with certainty would say that's the AI stained Raman image, and the other one is the real H&E, which is exactly what you want. In fact, you can go more in detail, because the pathologists, what they do, they annotate. You can see these red lines. They do an annotation of the images. So they say, these are the tumors. They do it by hand, they annotate. But then you can tell the AI, do the annotation for you. And so they do it for you. And the two look almost the same. But in fact, if you look carefully, even though the general distribution of the blobs is similar, the shape and boundaries of the blobs are not exactly the same in the AI annotated Raman image with respect to the H&E stained one. And of course, what we are saying is that the image on the right is much better, and the correct one with respect to what the doctor does, because it doesn't depend on a subjective opinion of the doctor. That is based on the Raman spectra collected for each point. But of course, at the moment, if somebody was to use that image for a diagnosis, it would be illegal, because this needs to be validated, and what we're going to do in the next few years. This is also interesting if you look at pharmaceutical. So you can map active pharmaceutical ingredients by this technique. So these are 6 pills of, in principle, the same chemical, the same medicine, built by 6 different chemical companies. And by using this Raman imaging technique, you can see, I don't want to go into the details, just look at it. Even though the pill is the same, the distribution of the crystals and so on is different company by company. And you can almost do a fingerprint for an individual company. So where are we at the moment? We have this system, the laser, the spectrometer, and the entire system. And now this is on sale. And it works. And the company is called CRI. And since last year, they're selling the system. And mostly, of course, at the moment for research purposes and in non-medical field, and as soon as this is approved, we're going to go in the medical field. I think my time is finished, but I want to spend another 3 or 4 minutes to to announce or explain this upcoming co-program partnership under Horizon Europe. I don't know if Albania is an associate country to Horizon Europe or not. Is Albania? Yes. So then it is definitely relevant for Albania. So what we're going to start on the 31st of January, well, actually on the 15th of February, there will be an official announcement with big PR and so on, is a new public-private partnership called Innovative Advanced Materials for Europe, IM4U. And this is a collaboration between the European Commission and an association that is called Innovative Advanced Materials Initiative. It's similar to the graphene flagship. The difference between the graphene flagship and this one is that the graphene flagship is a large European project run by a university. When you go to a partnership, you need an association that is self-standing under Belgian law, and this is the IMI. And so in order to be part of this, you need to subscribe to this association, and then you're part of the General Assembly, like it is in a normal project. It's a bit more complicated, but basically, on the 27th of February of this year, there was this announcement from the Commission, and the background, this is the press release, and it's based on the success that graphene had during the graphene flagship, and so they say we need to do something larger and bigger. Also, in the Draghi report that was recently published in page 62, there is a recommendation to increase funding and to build new partnership, this new partnership for advanced materials. On the top of it, in the mission letter given to the new commissioner for startup research and innovation, there is the sentence, you will work on Advanced Materials Act. So we are going to see in front of us this partnership that will invest 500 million between 25 and 27. So that's 2 years or 3 years, because then the money can be spent later. And compared to the 1 billion that the graphene flagship invested in 10 years. So the amount of money is way much bigger than what the flagship had invested so far. And also, we hope to continue this in FP10. So already in 2025, we'll start in 2026, we'll start a negotiation for FP10 until 2034. So the amount of money will be in the billions. And if the Advanced Materials Act goes ahead, you know what the CHIPS Act is and what the AI Act is. So if you know what large amount of money we're talking about. If an Advanced Materials Act is done, this will be way much bigger. On the top of this, there is the so-called Advanced Materials Academy that is going to be launched, the Advanced Materials Technology Council that will be announced soon. Because of the time is finished, I will just point you towards this communication of the Commission, Advanced Materials for Industrial Leadership. And let me go to 2 key points. The first is there are 4 main areas where the investment is going to be done on. It's energy, mobility, construction, and electronics. Electronics includes electronics, photonics, optoelectronics, quantum, sensors, and all this sort of stuff, but it's indicated as electronics. So as I mentioned, this IM4U in 25-27 will have an investment of at least 500 million. We expect this to be 625. The EIC is investing a lot of money. There will be a call of about between 25 and 50 million already in the next few years for SMEs. And let me skip to what are these innovative advanced materials. This is the new word, the new black, whatever. So innovative advanced materials are those materials driving innovation and new technologies. So there are 2 types. So enhanced forms of classical materials where properties are tuned for improved performance in specific application and total new application, or 2 novel materials enabling improved performance on new application, and graphene into the fitting number 2. And innovative means the commercial use or modification and functionalization on innovative ways to use classical materials. I also want to say that under the leadership of Austria, the process to have an IPCEI advanced materials has started. What is the IPCEI? Is an important project of common European interest. And I just want to give you as an example the one in microelectronics. And if you look, the amount of money is involved is several billions. So if there is a need change in advanced materials, it will be very large. So let me conclude to say that we are on the verge of something very exciting for Europe. For the first time, everything is aligned for what is going to be the largest step of investments and initiative in advanced materials, innovative advanced materials, 2D materials and so on, ever done in Europe and probably in the world. And as it happened with the graphene flagship, there will be a massive leverage, I'm sure, with similar initiatives started in the US. I was in China last week. They announced a similar initiative on advanced materials. So as a community, we have the new thing that is going to be called IMI, Innovative Advanced Materials Initiative, the new association. You need to subscribe to this association to be part of the General Assembly. And on the 31st of January, there will be the election of the Executive Board. And that at the moment, I co-chair the Transitional Executive Board, but it will be a two election then. And this association will be the counterpart of the Commission, will sign a memorandum of understanding, and the Commission will interact with this association in order to define all the investments of the next few years. You will see already for 2025, around 85 million euros being invested in programs that the Transitional Board has requested the Commission to work on, and these cover flexible electronics, they cover composites, they cover construction, and photonics, of course, all of these advanced materials for photonics for with low energy consumption. And I will stop here, thanking all the collaborators, in particular, Giulio and Matteo for the laser. Thank you very much.
Thank you very much, Professor Ferrari. Thank you very much for this amazing talk and all the initiative you are coordinating. AMI initiative is really very, very important for all the countries in Europe and particularly for Albania and the region. So we have time for one question from the audience for Professor Ferrari. Is anyone willing to ask, or you can also use during the coffee break? So please.
Show a signal 2008, which is CH3 from problems.
Yeah.
This shift. Why is that?
Yeah, so in the example I showed here, I only showed the CH region. There is also the fingerprint region around 1600, and different kinds of cancers have different kinds of signature for different kinds of molecules. So I could have spoken 3 hours about that. I just give you some examples where you can see lipids and proteins and so on. The theory, or let's say the background on how to detect cancer with Raman is not something that we have done. As I stressed, this has been done in the past 20 years plus by many, many people. So there are different molecules and markers that you can check. It is not very common it's not used at all in hospitals because it takes forever. So we are simply using, and there is actually a database of cancers, an official one in the UK. We are doing what is called all the qualification steps that are required in order to be actually used for real in the medical field. Yeah, it is typical. We are not looking at the shift at the moment, we are looking at the intensity ratios. But you also know that the shifts have meaning, but at the moment, all what I'm showing is intensity ratios, intensity. And they are all collected under the same instruments very quickly. So the problem of disalignment and so on that you typically have in spontaneous Raman don't exist. So this is pretty accurate. But I mean, I chopped off 90% of the total, so I can give you much more detail later.
Okay, so let's congratulate again Professor Ferrari. Thank you very much for the big talk. Okay, so now it's a pleasure to welcome another Greek scientist and colleague and friend, Professor Michal Otejka, who is the head of the katërtin PTM Research Division at Palaski University in Olomouc, Czech Republic, and who is leading the Laboratory for Modeling and Nanotechnologies for Innovations and Technical University of Ostrava as well. He's also a member of the scientific board of the Czech Grant Agency with a lot of achievements, activities in graphene, 2D materials, and photoluminescence properties. Carbon dots is going to speak today for graphene derivatives with great publications and projects. He's a ERC holder, consolidator grant, 3 ERC proof of concept grants, EIC transition grant, and more. A lot of publications, 300 publications with a lot of citations and impact. So thank you very much, Misha, for coming again. It's your 4th time, right, in Albania? So I'm very happy to have you here. Thank you very much.
Thank you, Arben, for very kind words, and I'm really happy to follow the great talk by Andrea Ferrari about the graphene. And let me continue about the, let's say, engineering of graphene derivatives for many applications, and I'll focus on the sensing applications in my talk. So why I'm speaking about the sensing, and I guess that you understand the importance of the sensing, and because the information is the power, and what we really need is to get information about the healthcare, about the health for healthcare applications, about the environment for, let's say, environmental protection, about the quality of environment, about potential pollution. We also need information about the industrial processes, again, due to control industrial processes. Well, there are also many applications related to the biosafety and welfare application, etc., etc. And what is really needed is to have the information handy, on time, and very quickly available to have a broad picture about the analyzed system. And to achieve this, there are many, let's say, tools developed so far, but we have to continue with development of those tools for various, to broaden the application portfolio. And definitely you are probably familiar with some of those, let's say, devices which can be based on, let's say, point-of-care devices, which we can use as the monitor glucose, let's say, the blood, which is also very, very useful and can provide very quickly information about the health conditions when needed, let's say, for the treatment, to treat the diabetes. There are also requirements concerning properties of such sensors, which are given by the Organization of Health, and they are listed over there. So definitely we need real-time, affordable, cheap, easy-to-use devices. So we speak about that. We need to have such devices assured. And it can be realized very nicely by electrochemical sensors and electrochemical biosensors. And let me briefly introduce the electrochemical biosensors, because the concept is really easy. You have to have something which transfers the electrochemical signal to a readable, by computer or in a readable form into data. Then we need the transducer, so which is a material transducing the interaction of the analyte with the electrode. And then we need something which provides the selectivity. And usually for the selectivity, we use the biocomponents. There can be a broad portfolio of various biocomponents which can be used for the construction of biosensors and sensors, which can range from the antibodies. It can be, let's say, nucleic acid aptamers, even the small cells, etc., etc. Also, there is a big progress concerning the miniaturization, and it's really important for future. So definitely the classical potential stuff, let's say, used in the labs can be miniaturized into very small devices which can be used also, which can be, let's say, plugged to the mobile phones, this display down on the slide, or you can even establish a small devices which can be also removed and distributed for the sensing, let's say, in the fields. So the key component of those devices are the bioreceptor, which are available, and or they have to be tuned for particular sensing applications. And also we need to have a very good transducer. And following the ideas which were introduced concerning the graphene as a beautiful material, we can use the graphene, but we have to modulate the graphene to be useful for such biosensing applications. Because naked graphene is great material, as we heard, but definitely for the sensing applications suffer from a small drawbacks which we would like to improve. And in principle, we can modulate graphene properties by two modes of modulation or functionalization if you want. And we can work with the so-called non-covalent way of graphene functionalization or covalent graphene functionalization. There are big differences in between two modes because the non-covalent graphene functionalization means that we use a graphene, which is, let's say, which interacts with some gas molecules. As a prototypical example, it can be pyridine butyric acid. And on this acid, you can bind a biocomponent and you can establish together the devices which are very sensitive and selective toward, let's say, the diseases, as was demonstrated in ACS Nano and also over this paper over there. But for the non-covalent functionalization, there is always a risk of the material disintegration and, let's say, stability of such devices. So then we can use the covalent functionalization, and there are many approaches how to functionalize graphene, but it is not easy because graphene itself is a quite unreactive material because it's a carbon-based lattice of sp2 carbon atoms with an aromatic ring, so it is a formally infinite polyaromatic hydrocarbon, and it is very hard to chemically modify such materials. So we have to use a very harsh chemical conditions to modify graphene, and it usually leads to such material like a graphene oxide. Well, graphene oxide is a great material. We can use it because it's a water dispersible. We can use for spraying, let's say, making the screen printing electrodes, for instance, etc., etc. But it is a non-conductive material, and if we would like to improve the conductivity of graphene oxide, we have to reduce graphene oxide. We can use a chemical or thermal ways for graphene oxide reduction to something which is more conductive than graphene oxide. But in principle, we can also bypass the unreactivity of the graphene by utilization of another material which is also graphene derivative, which is called fluorographene. Fluorographene was introduced in 2010. And it is available in a large scale because in principle, its pristine material is a graphite fluoride. And graphite fluoride is used from, let's say, 1760s as an industrial lubricant or also in the electromaterial for the primary lithium batteries. And if you exfoliate graphite fluoride or graphite into one layer, you get fluorographene. And fluorographene is a perfluorinated hydrocarbon. It seems at the first glance that it shouldn't react because it chemically resembles slightly, let's say, Teflon. And we know that Teflon is quite stable material, but it's reactive material because all the fluorines are attached to the tertiary carbon atoms, and such fluorines or CF bonds are susceptible for modifications. And we can use easy way, and we can work at a quite controllable chemical conditions. And always we observe two reaction channels. On one hand, there is an elimination channel, and on the other hand, there is a substitution channel. Elimination channel means that some fluorine atoms are removed from the structure, and then we re-establish the sp2 conjugation inside the graphene lattice. So it leads to the increasing of the conductivity of such material. And the substitution channel means that some of the fluorines are replaced by something else, like chemical functionalities, which can be further used for many various applications. And so far we were, and also many other colleagues over the globe, were able to mount various functionalities on top of graphene in a controllable way. We can also synthesize graphene, which is functionalized on one side, so-called Janusz-style graphene. We can also develop chemistry which leads to the very facile modification in the lattice. So we can synthesize also hydrogen-nitrogen doped graphene in the lattice by the fluorographene chemistry. And this is just the overview of the graphene derivatives you can obtain. You can make a snapshot so you can find all the references inside the publications. And just to simplify the thing, so in principle, the chemistry we develop leads to the graphene, which has organic functions. And organic functions enables us to use the organic chemistry to mount whatever we want in principle on top of graphene. It can be another organic functions, they can be biomolecules, they can be metals, they can be metal nanoparticles. And it dictates or enables us very broad portfolio of materials for an amazing scope of the materials which can be used for broad portfolio of application. I'm going to speak about it later. This is the one working example together with Aris, we published in 2017 in ACS Nano. So this is the example of synthesis of so-called cyanographene. So it is mounting of cyano group on top of graphene. So we use the fluorographene. We treat it with the sodium cyanide at 130 degrees in DMF, but you can also replace DMF by something more eco-friendly. And you can see that during the course of the reaction, CF bond diminish or reduce, and also they appear the C N bonds, so nitrile bonds inside the lattice. If you look at the EDS map, you can see that the nitrogen is homogeneously spread over the graphene lattice, which means that the functionalization spreads over the graphene surface. And also the chemistry is beautifully scalable. So this is the demonstration of the reactor we use for the synthesis. So the batches are around dozens of grams. So we can synthesize these materials at the level of the dozens of grams, and we can upscale up to the kilos. Well, if you have, let's say, nitrile group, you can also functionalize it because, let's say, nitrile group, and this is just the demonstration of the beauty of organic chemistry, can be modified to the carboxy group by the easy hydrolysis under acidic conditions, and then you synthesize material which we call carboxylated graphene or graphene acid easily. And it resembles the properties of the organic acid, but is a two-dimensional, formally two-dimensional acid. It behaves like it has a beautiful titration curve with the pKa around 5.3. Below the pKa, it starts to precipitate, so you can use also for the, let's say, some metal harvesting purposes. It is a colloidally very stable material at a high concentration as well as a low dilution. It is also electrochemically active, as you can see at the cyclophotometry probe. So this material which is electrochemically active and can be used for, let's say, electrochemical sensing applications. And well, it has a carboxy group, and carboxy group enables further chemistry. And in principle, we can use, for instance, carbodiamide chemistry, and we can mount various functionalities using the carbodiamide chemistry. And one day, or at the end of the day, you can have a graphene with ending group, which can be SH, NH2, OH, whatever you want in principle. So this is the working example. We also pay a lot of attention to the standardization. So the graphene acid is available on the market, you can purchase it. And the batch-to-batch variability is very low, which is very advantageous because, for instance, sometimes the batch-to-batch variability spoils many practical applications if you buy the, let's say, graphene oxide from the providers globally. And standardization of graphene and graphene derivatives is one of the major challenges in this field. So this is just the concluded first part. So definitely this is the scope of the fluorographene or even graphene derivatives obtained by fluorographene chemistry. And you can see a very broad portfolio of applications because we can produce a very broad portfolio of graphene derivatives by this chemistry. And we can touch such applications like the environmental applications, catalysis, single atom catalysis, biomedical application, energy storage applications, sensing applications, and definitely also we can play with the magnetism and spin states in the essential graphene derivatives. Well, I'm going to continue about the sensing applications, but there are also following talks by Professor Alice Božio, who is speaking after me after the short break about the mostly bio application, if I'm correct. And also Aris Bakandrito is going to speak this afternoon, if I'm correct, about the energy storage applications. So you can see the broad portfolio of applications of graphene derivatives even today. So let me continue with the sensing applications, and this is just a couple of examples where we apply graphene for sensing applications or graphene derivatives. So we were able to sense the temperature. I'm going to present this example. Ions, organic material, organic molecules, let's say, antibiotics. I'm also going to speak about this application, and very briefly I will also touch the DNA sensing for the media direction detection. So temperature sensing is really important for the many practical applications. You'd like to know about the temperature inside, let's say, buildings, etc., etc. There are also many sensors developed so far for the thermal sensing. And usually what is the issue concerning the thermal sensing, if we miniaturize the sensors, is the interference with the humidity. And relative humidity can spoil the sensing, the response of the sensor. And it is, that's why from the many practical applications, we have to, let's say, box the sensors to avoid the interference with the humidity. But if we box something, we usually spoil also the dynamics. So how rapidly the sensor reacts to the changes of the temperature. So just to develop materials which can stay, let's say, naked, to be directly exposed to the environment and which do not interfere with the relative humidity is a challenge. So concerning this challenge, we developed a material which can sense the temperature, but which is free of the interference with the relative humidity. So by mounting of the functionality based on the benzylamine, we developed the various materials. And this is the geometry which we use for the sensor. Well, maybe there's no need to speak about the details technical. There is a very nice response, very nice dynamics of the sensor. We have chosen the material which doesn't show any interference with the relative humidity, as shown in the lower plot. Sorry, because laser doesn't work here, so sorry, I cannot easily show you. But you can see that there is a red curve which is not sensitive for the relative humidity, because this is the temperature sensor or response with respect to the level of the relative humidity, and you can see that the red curve is almost insensitive. So this is a suitable material for the development of temperature sensor with relative humidity insensitive, and also the very safe operational ranges defined by the green parts of the curve. So in principle, by the development of the graphene derivatives, you can develop materials which can sense such physical properties like the temperature, avoiding easily also the potential interference happening in the systems, like in this case, relative humidity. So let me dive back to the biosensing, and I already mentioned that in principle, constructing the biosensor, we need three components. We need readout, we need a transducer, and we need a bioreceptor. It is always very advantageous to establish a covalent link in between the bioreceptor and the transducer, and we can easily utilize the chemistry of graphene. So this is the working example. You can take a graphene acid having the carboxy groups, then you can take the bioprobe. In this case, it was an aptamer, which was also functionalized by the redox probe. And we decided to use the click chemistry because the click chemistry is very sensitive, very selective, and also it can be realized at a very ambient temperature with a very high yield. And in principle, by combining the aptamer probe functionalized with the functionalized graphene acid, so we worked with the graphene acid which was functionalized by the propalkylamine. Then we made a click chemistry. We covalently attached the aptamer to the sensor, and then we modified the electrodes. In this case, we used the classical electrodes provided commercially. Maybe there is no need to go into the details and characterization. So this is the chemistry what we used in the schematics. We also very carefully calibrated everything, and we selected the proper electrochemical response. On the bar plot, which is, let's say, in the middle part of the plot of the slide, you can see the selectivity. So we used the aptamer, which was selected for ampicillin, the antibiotics, and you can see the very high sensitivity, as well as the selectivity, which is exclusive to the ampicillin, as dictated or given, if you want, by the aptamer used. And also, you can directly use this biosensor for the detection of the ampicillin, let's say in saliva or milk, which is really important. And concerning the sensitivity of the sensor, it is sensitive enough to be below the threshold of the limit of the ampicillin in the milk. And let's say detecting of the exposure of various foods as well as environmental to the antibiotics is really important to also mitigate the potential one of the biggest problem of the whole global society, which will be the antimicrobial resistance. Because, well, let's say it is expected that in 30 years, the rate related, or the death rates related to the microbial resistance will be similar as the death rate related to the cancer today. So, because many strains of the bacteria are resistant to various antibiotics in the market, and there are two mitigation strategies. One is to reduce the usage of the antibiotics, and the other strategy is to develop different antibiotics, and this is what Radek is going to speak about later. So this is the working example. What is the beauty of this strategy is that we develop a technology which can be easily modified. So if you use the same chemistry, you can just change the aptamer, and then you can develop a selective and sensitive sensor for, let's say, various antibiotics or various molecules in principle. So this is very versatile chemistry which can be used. Then later on it can be also miniaturized, because also the potential stance can be very small, like those shown. Maybe there are also other talks from the ICM2 about the miniaturization in this field, because there is a great progress also in this field of the biosensing. So very briefly, this is also another working example. So in principle, you can also work with the DNA hybridization, and you can establish the sensor response based on the DNA hybridization. And you can use, for instance, to identify that, let's say, the declared beef meat was contaminated by the pork, because pork is cheaper. So, and in some regions, it's an issue, especially in South America. So, well, I also show one example. We can modify the available electrodes, which are commercially available, and those electrodes use the ceramics. And let's say for the broad application of such electrodes, there are questions related to the disposal of such electrodes after the measurement, because this is based on ceramics, there are metals, there are plastics, so, well, they live with us forever. Well, what about to replace such electrodes by something which is more, let's say, disposable or more sustainable? And in principle, we need to develop technologies which can use our materials, and there are many technologies can be used, let's say, for the printing. And we have selected the inkjet printing because it is a digital technology with almost zero losses. It can be easily, let's say, utilized in principle, because there are also many various commercially available inkjet printers. So it can be also what is called today democratized. So in principle, anyone over the globe can easily develop the let's say, sensors or electrodes based on the inkjet printing technology. What we need for the inkjet printing, just three things. So inkjet printer support, I mean, let's say paper or plastics, so what we print on, and also ink. And the most challenging part in this field is to develop ink, because they are the requirements given mostly by the printhead or the printing technology, which is usually based on the piezoelectric effect, and the ink is printed through the needles. We have to avoid the clogging of the needles, which dictates the material size. So the individual flakes of such graphene derivatives must be smaller than, let's say, half of the microns. Well, there are also the other physical properties dictated by the printhead about the, let's say, viscosity and surface tension. Definitely what we require is that such inks are stable for a long time. And they also have to have enough adhesion, and they also have to display the electrochemical response. So, well, we developed a material which I presented that can be used for electrochemical sensing and electrochemical biosensing. So the challenge was to reduce their size to be compatible with inkjet printers. So by chemistry, it was developed by David Panachi, who's over there. We developed a technology how to shrink the size of the individual flakes to the reasonable size, and then we can use such materials. And this is also the AFM figure of such material. So you can see that the lateral size is definitely around the micron size, say this, the micron size, and also you can see the vertical size of such materials. We can print such materials on top of the commercially available electrodes, and we also establish inkjet printing of the whole electrodes, which contain not only our working materials as a working electrode, but also all the lining, also the counter electrodes, etc., which are based on the metals and available metal colloids. So in principle, this is just the electrochemical characterization of those electrodes which we were able to develop, and maybe the central panel down shows the electrochemical response. In this case, it was a neurotransmitter, and you can also see how the electrode was printed. So it is the July 23, and due to progress done by my staff, mostly by Martin Alex, who is also here, we were also able to beautify those electrodes to the style, which is also shown, let's say, for summer 2024, and also the support of the ERC project is also mentioned by Arben. So let me conclude the talk. So I hope that I persuaded you that by the beauty of the chemistry of the fluorography, you can synthesize a large portfolio of graphene derivatives which are well suited for a large portfolio of applications, those also including the biosensing applications. I also hope that I persuaded you that the inkjet printing technology is a very efficient method for fabrication of the working electrodes, which are also more sustainable and useful for the sensing, electrochemical sensing and biosensing applications. And definitely there are also many questions which have to be answered for future about the electrode composition, about the real nature of the electrodes, which is also from the characterization point of view quite challenging task. And at the very end, I would like to thank all my coworkers, collaborators. Definitely also I would like to mention Arben Merkoci. And I'm really proud that Albania is also proud of Arben, because Arben does a lot for promoting Albanian science and networking Albanian researchers. Also, we have a couple of the projects with Albania, and I would like to highlight the projects labeled Susnama project. Also, there are the results of modified electrodes based on the collaboration between the University in Tirana, our institute, and also ICM2 in Barcelona. And I would like also to thank all the brand agencies, and I would like to thank for a very kind attention. Thank you.
Thank you very much, Michal, for the very, very interesting talk. We have time for one question now. Who is willing to ask a question? So.
Thank you very much for this amazing talk, Professor Michel. I wanted to know just about the thickness of this carboxylated graphene. Do you have the entire film with the same thickness? Thank you very much.
Well, not exactly on my presentation. I can show you later on the real thickness. So, for instance, if we print 20 layers of the electrode, the thickness is roughly 160 nanometers. So I can show you also the real electrodes, and also the cross section, and also the analysis by the microscope.
Okay, so let's thank again. Thank you very much, Michal, for this very interesting talk. Thank you very much. So we have the last speaker for this session, and it's a pleasure to welcome now Professor Ese Eksin from Izmir Democracy University in Turkey. And Ese is going to speak about electrochemical microRNA detection using gold decorated reduced graphene oxide. Thank you very much, Ese, for being here, for coming in Tirana.
Thank you very much, David. So, hello everyone, and I am Associate Professor Ece Eksin from Turkey, and today I'm going to talk to you about microRNA detection using a 2D nanomaterial-based biosensor. So this project was supported under Nito funding program, and the project coordinators were Professor Arian Jaupllari and Professor Pagano Papa Constantinou from UK. Today I would like to dive into the fascinating world of electrochemical nucleic acid biosensors. You may be wondering why we choose this type of biosensor, because it has some unique properties, the advantages over other type of biosensors. Basically, they can perform continuous measurements, and they are inexpensive, portable, and they have, they provide on-site measurements, which are requirements of the future healthcare, actually. MicroRNAs are small non-coding RNAs, can be found in eukaryotic cells, and these informative biomolecules are stable in serum, and they have critical roles in variety of cellular processes, and they can be oncogene or tumor suppressor genes according to the inhibition sites of the mRNA, if it is oncogenic part or tumor suppressive parts. And they play major role in diagnosing specific types of different type of cancer. So in this work, we used microRNA 21 as a biomarker for non-small cell lung carcinoma, and microRNA 21 is overexpressed in variety of tumors, and it's oncogenetic microRNA, we can say. So in our project, we use reduced graphene oxide, and the reduced graphene oxide is one atom thick graphene structure with a reduced oxygenous species, and it has high electrical conductivity. It provides high surface area, and some defective sites provide its chemically active sites for the modifications, and actually they are biocompatible and cost effective, we can say. So, and also, as I mentioned, it was a 2D nanomaterial. We covered the reduced graphene oxide by gold nanoparticles. So, the gold nanoparticles are also a very good nanomaterial in this field. So they also provide large surface area, and they have high chemical stability, biocompatibility, and due to low toxicity, we can use it very much. So in this work, we used sustainable paper electrodes, and they have many advantages over common electrodes, and they are flexible, they are user-friendly, and it's very easy to use. They are disposable, and they provide high sensitivity and good reproducibility, etc. we can say. So, the design and the fabrication of the electrodes were unique for this project. And here you can see the design steps. So for the hydrophobic barriers, we used wax printer. So, and after that, the carbon ink was applied for the carbon working electrode and the counter electrode, and followed by silver silver chloride ink as a reference electrode. And for the barriers, we cured these electrodes at 100 centigrade degree for 5 minutes, and then the electrodes were ready to use. And the overall of this, our work is to establish a novel approach for electrochemical detection of microRNA 21, which is a good biomarker for early diagnosis of non-small cell lung cancer using these gold decorated reduced graphene oxide modified paper electrode. We can basically divide our work in 3 steps. So in the first step, it includes generation and the modification of paper electrodes. In the preparation of paper electrodes performed by our colleague in different university, Gazi University, and so I will not go on to the details in this part, but after we obtained these electrodes, we used modifications and the detection part, and I will talk about them, these parts. So, after modification of these electrodes, we use them to detection of microRNA 21, and finally, we perform electrochemical measurements for the detection of hybridization. So here is the details of our material, the methods. And we started with the modification of the electrodes, of course. So these are the electrodes we have, and the working electrode surface area covered and drop casting by reduced graphene oxide. And then the EDC NHS was used to activate the surface area as a cross-linking agent. And then the reduced graphene oxide surface was applied by a gold precursor solution, and the covered and the electrodeposition technique was used to cover the surface using chronoamperometry technique. In the second step, after we modified our electrodes, the DNA probe, which is tile-linked because we have gold nanoparticles on the surface, and DNA probe immobilization was performed by drop casting during 30 minutes, and then the target was applied for the hybridization during 5 minutes. At the end, the DPV measurements are performed. Our electrode was ferrocyanide redox probe solution. So we measured the oxidation signal of this redox probe. So what we obtained, first we measured in the absence of any probe and any target molecule, only the paper electrodes, and the oxidation signal was measured. And then when we covered the electrode surface with the probe solution, due to the negatively charged DNA molecule, the signal decreased because of the hindrance of the electrodes between electrolyte and the electrode surface. And then when we continue with the hybridization, this signal decreased again due to the highly negatively charged DNA molecule at this time. We have a hybrid structure, and it's more negatively than probe. So yeah, based on this phenomenon, we investigate our results. So firstly, we started with the characterization, and here you can see the reduced graphene oxide SEM image, scanning electron microscopic image, and on the right you can see the SEM image of the paper electrode covered by the reduced graphene oxide at the A, and the reduced graphene oxide and the gold nanoparticles in the figure 3B. So the size of gold nanoparticles were calculated at 229 nanometer, and it was seen in this image. These gold nanoparticles are covered both reduced graphene oxide surface and the working electrode area. And next, in order to investigate the electrochemical behavior of these unmodified or modified electrodes, we use cyclic voltammetry technique. And so we measured using all type of electrodes, unmodified one, reduced graphene oxide modified one, and gold and reduced graphene oxide. modified one and compared the anodic and cathodic peak currents. When we see the 3D nanomaterial modified electrodes, the anodic and cathodic peaks were, the peak currents were very high according to the unmodified one. And after that, using these signals, we calculated the electroactive surface area using Randall's equation. And there was 80% increase in the electroactive surface area in case of reduced graphene oxide and gold nanoparticle. So all of the experimental conditions were optimized. As prop concentration, prop immobilization time, and hybridization time. So all of these results can be found in our paper. So under optimized conditions, we performed the hybridization between capture probe and microRNA 21 target sequence, and in various concentration between 0.25 and 2 microgram per milliliter. So in case of 1 microgram per milliliter target sequence, the lowest signal was obtained. And the limit of detection was calculated as 12 nanometer, which is equal to 6 femtomole in 5 microliter sample. And next, selectivity of the assay was tested in the presence of non-complementary and the mismatch sequences, which has only one base difference from the target sequence. And also we tested our selectivity in the presence of mixture samples, so which contains both target and non-complementary or target and mismatch sequences 1:1 ratio. And in case of full hybridization with our target microRNA, we had the lowest signal, and we can say the selective behavior is obtained even in the presence of unwanted sequences. So in summary, in our work, we achieved high reproducibility and signal amplification by incorporating reduced graphene oxide nanosheets and gold nanoparticles. And using voltammetrically, we can detect, and using voltammetric technique, we can detect microRNA 21 only in 35 minutes, and a very low sample like 5 microliter. And our assay was cost-effective, user-friendly, and time-efficient, and it required minimal sample preparation. And yeah, we can say paper-based electrochemical biosensing platform is designed to be affordable, portable, and eco-friendly in this work. Yeah, and I would like to thank to my former supervisor, Professor Dr. Arsimit, and our team members for their great collaboration, and thank you for your kind attention.
Thank you very much, Professor Axin, for a very nice presentation. We have time for one question only. Is any question, please?
Thank you for a very nice talk. I have just one question. What about the nature of the interaction between gold nanoparticles and graphene oxide? So meaning, what about the possible leaching of gold nanoparticles from the electrode surface?
Actually, we use, the chronoamperometric technique, which makes it very stable, and we haven't seen any etching, any difference, because the probe solution, it's an aqueous solution. When we drop casted it, nothing changed on the surface. So it was really good, actually.
Okay, so thank you very much again. Thank you very much for your presentation. Thanks for being in this session. And now we are late, so please let's have just 20 minutes of coffee break and be back here at 11:40.